Hi everyone, I hope you're doing good. Today I will show you how to perform multi-step LSTM time series forecasting. This video is based on my original article on how we apply advanced deep learning multi-step time series forecasting with the help of this template. In my previous article, we have seen multivariate LSTM that have multiple inputs for LSTM to forecast the time series data. Now here in this video, we will take one step further with stepwise forecasting. For this example, we will forecast for 3 months. As we all know, the difference between the LSTM and RNN, LSTM is the next generation of recurrent neural network, that is the RNN, used in deep learning and for its optimized architecture to easily capture the pattern in sequential data. The benefit of this type of network is that it can learn and remember over long sequences and doesn't rely on pre-specified window lagged observation as input. In Keras, this is referred to as stateful and involves setting the stateful argument to true in the LSTM layer. Now, LSTM includes 3 important gates: input gate, forget gate, and the output gate. Input gate decides which values from the input to update the memory state. Forget gate handles what information to throw away from the block, and the output gate finally handles what to be in output based on input and the memory gate. There are a lot of articles available on the internet about the working of the LSTM and even the math behind the LSTM. So here I will concentrate more on a quicker implementation of the LSTM to meet our day-to-day solutions. First, we will call all the important libraries. Then we will define functions to convert the time series into supervised learning problems. The next step is to convert the time series data to stationary. And our cells_year.csv data is not stationary. This means there is a structure in the data that is dependent on time. We can see there is an increasing trend in the data. Stationary data is easier to model and will very likely result in more skillful forecast. The trend can be removed from observations, then use for forecast later. We can scale it to the original value for the prediction. We can easily remove a trend by differentiating the data with diff function from the pandas. That are the observations from the previous timestamp t-1 is subtracted from the current observation. This gives a series of differences. Now it's time to normalize, scale the data. LSTMs are a bit sensitive to the widespread scale of data. Even in all deep learning models, scaling the data range of -1 to 1 before fitting it to our algorithm is a good practice to keep the algorithm to work faster and effectively. And yes, scaling the data will not lose its original meaning from the data. We also call this as normalization using the min-max scalar preprocessing class function. Even the default activation function for LSTM is the hyperbolic tangent 10, which outputs values between -1 and the 1, which is preferred range for the time series data. Then we'll split the data into train and test. It's time to deploy the LSTM. By default, an LSTM layer in Keras maintains a state between the data within one batch. A batch of data is fixed number of rows from the training dataset that defines how many patterns to process before updating the weights of the network. By default, state in the LSTM layer between batches is clear. Therefore, we must make the LSTM stateful. This gives us fine-grained control over the state of the LSTM layer when it is clear. LSTM network expects the input data X to be samples, timestamps, features format. Batch underscore input underscore shape equals to n batch x dot shape 1 and then x dot shape 2. The batch size of 1 must be used since we require prediction to be made at each time step of the test dataset. And the number of neurons, also called memory units or blocks. Then we have the one output layer dense. In the compiling network, we must specify a loss function and optimization algorithm to calculate the loss and the weight. This is just our regular LSTM stuffs that we have learned from our previous chapter. Now, E and F are the functions to predict the next 3 time sequence. Then G and H is the inverse, the forecast value to our original dataset value. Remember, we have scaled value with min max scalar and then difference series to remove the stationary trend. Finally, we will calculate the root mean square error RMSE to understand the accuracy level, and at the same time we will plot our 3-month forecast. Running the code will give you the plot and the RMSE score. We can notice that the RMSE does not become progressively worse within each forecast. This is because the T plus 2 is easier to forecast than the T plus 1. The plot also depicts the model needs improvement over the LSTM. There's plenty of room for improvement. Let me know if you are able to improve the model. I have added all the articles and all the resources in the description below. I hope you find this walkthrough useful. Thank you. See ya. Bye.